Well, so this is the second half of Math 253, and we're going to talk a lot about sequences and series. And so sequences and series are usually talked about together. I think the main reason for that is that to find the limit of a series, or to find the sum of a series, you sometimes have to look at the sequence of partial sums. So let's just talk about that briefly, and then we'll get into what's happening on the worksheet. So let's say we have a series of 1 over 2 to the n. Yeah, right. I'm not supposed to use n for the index here. I'll use I as I runs from 1 to infinity. Okay. So this is a series, so it's a sum. Let's see here. This will start out with a half, a fourth, an eighth, a 16th, and so on. Okay? So often what people do to find the sum of a series is that they look at what's called the sequence of partial sums. Okay? So the first partial sum is just the first term. The second partial sum is the sum of the first two terms, and so on. Okay? A half, a fourth, and an eighth. That will give you 7/8. And then this one is going to be 15/16, and so on. And so S sub n here, the nth partial sum, is going to be, what is it? It's going to be 2 to the n minus 1 over 2 to the n. So here you have a series, which is the sum of all these terms, but like I said, frequently if you want to know where this sum is headed to, what is the sum of the series, it's helpful to look at this sequence of partial sums to see where this is headed to. And this is headed to, if we take the limit of S sub n as n goes to infinity, that should give us 1. Okay? All right, so there's an example of the relationship between sequences and series. So we're going to start out just talking about sequences in isolation and get a sense for how these work at a fairly basic level. Okay, so let's see. On the handout, on the front side of the handout, I'm just asking you to list the first 5 terms of the sequence. Like I said, this is at a very basic level, just getting used to the notation and what we're talking about here. Okay, so if we want 5 terms, a sub 1, so we just plug in the 1 for the n. So it's 3 to the first on top, and then 1 plus 2 to the first on the bottom, and then we can reduce it. For 2, a sub 2, we're going to have 9, and then 5 on the bottom. A sub 3, it'll be 27, and then 1 plus 8 on the bottom, so that reduces to 3. A sub 4 is 81 over 17. And then the 5th term of the sequence is going to be 3 to the 5th power, which is 243, over 2 to the 5th, which is 32, plus 1, which is 33. So this should be 81 over 11. And that's all we're looking to do in these problems. It's just, like I said, just get used to the notation and how this works. We're just plugging this number in for the n and then making our calculation. Okay, so that's problem 2. Let's see here. Problem 4. We've got a sub n is cosine n pi over 2. And you can do this on the calculator if you'd like. I frequently use the unit circle to do this, right? Where this is 1, 0, 0, 1, negative 1, 0, 0, negative 1. And here the x-coordinate is the cosine, the y-coordinate is the sine. Okay, so if we want cosine of 1 pi over 2, then that's going to be 0. And then cosine 2 pi over 2 is the cosine of pi, so that's negative 1. A sub 3 is the cosine of 3 pi over 2, which is again 0. A sub 4 is the cosine of 4 pi over 2, which is cosine 2 pi, which is 1. And then the last one, a sub 5, well, the last one for this exercise will be another 0. We're just going in a circle like this. It's just going to repeat these 4 numbers, 1, 0, negative 1, 0, and so on. Okay, so that's problem 4. Let's see here, problem 6. Okay, problem 6 has an interesting feature in it, and this is that negative 1 to the n power, and then we've got an n, and then n factorial plus 1 on the bottom. If you've never worked with a factorial before, it's just this number times all the numbers smaller than it. So like 5 factorial is 5 times 4 times 3 times 2 times 1, which gives you about 100, which gives you 120. These factorials grow very large very quickly. All right. They're used a lot in discrete mathematics, in methods of counting and combinatorics. So let's see here. All right. So the interesting thing in problem 6 is this negative 1 to the n power. Because what that's going to do is that's going to make this, the value of the sequence term bounce back and forth between being positive and being negative, right? Every time the n is an odd number, it'll be negative. And every time the n is an even number, it'll turn out positive. So, a sub 1, this will be negative 1 to the first power, which is negative. The n is 1. And then on the bottom, 1 factorial is just 1. 1 plus 1 is 2. Okay, there we go. For a sub 2, this will be positive. 2 on top. 2 factorial is 2 plus 1 is 3. This will be negative 3 on the top. On the bottom, let's see, 3 factorial is going to be 6. 6 plus 1 is 7. A sub 4, let's see, that'll be positive 4 on top. Let's see, 4 factorial then is going to be 24 plus 1, 25. And then the a sub 5 will be a negative 5 on top. And then that 5 factorial we said was, 120 plus 1, so 121. Okay. With this negative 1 to the n power, if you want your first term negative, you can use the n. If you needed the first term positive, a lot of times you can use an n minus 1 or an n plus 1. We'll see that in one of the problems on the back of this handout. Okay. All right. So that's problem 6. Okay. Problems 8 and 10 are what are called recursively defined. It's a recursive definition where they give us some of the terms for the sequence, and then they tell us how to calculate the next term based on the previous one. Okay? So if we want A2, then we go back to A1. That's the numerator. The value of n is the denominator, and so that comes out to be 3. Okay. A3 is going to have A2 as the numerator, and then the value of n as the denominator. And so we'll just keep going like this. That'll be 1/4. And then a sub 5 will have 1/4 on top, a 5 on the bottom, and so that comes out as 1/20. Okay. And then let's see, problem 10. We've got a sub 1 is 2, a sub 2 is 1, and each term is going to be defined by the difference of the two previous terms. So, if we want a sub 3, that's going to be a2 minus a1, which is negative 1. And then a4 is a3 minus a2, or negative 1 minus 1, which is negative 2. Let's see, yeah. And then a5 is going to be a4 minus a3, negative 2, oops, minus negative 1, and that'll give us negative 1 again. This is kind of an interesting little sequence. It eventually does repeat itself. So I just found that kind of interesting. Let's see here. There's a famous, probably the most famous recursive sequence is what's known as the Fibonacci sequence. And this comes from the Italian mathematician Fibonacci, who wrote a book in 1202 called Liber Abaci that was all about calculating. And his father was his father represented the merchants of Genoa, Italy, across the Mediterranean in North Africa. And so he took his son, Fibonacci, over to North Africa with him in the 1100s and hired an Arab math tutor for him. At the time, Europeans were still using Roman numerals. Okay, the Hindu-Arabic numeral system that we use today was developed in India and then transferred into the Middle East sometime around the 7th or 8th century AD, sometime in there. That was the golden age of Islamic math and science, was that period of time. So anyway, in the 1100s, Fibonacci learned about this number system and the methods that we learned in elementary school to calculate with these numbers, and he put it all in this book called Liber Abaci. He also put a lot of algebra in there, and then he also put this problem about the growth of a population of rabbits, and that leads to what's called the Fibonacci sequence, where A1 is 1, A2 is also 1, and then A sub, let's see here, A sub n, I'll call it A sub n plus 1, is going to be A sub n plus A sub n minus 1. So it's the sum of the two previous terms. So then A3 is 2, A4 is 3, A5 is 5, A6 is 8, A7 is 13, 21, 34, and so on. What's interesting about the Fibonacci sequence, once we write it out like this, is that if you take the ratio, the limit of A sub n over A sub n minus 1 as n goes to infinity is actually the golden ratio, which mathematicians use the Greek letter phi to represent. So you can here's 1.6 right here, and then if we do 13 divided by 8, I think that's going to be 1.625, and so it's approaching this 1.618 value. Okay, let's look at some of the problems on the back of the page. So in these problems, we've got a sequence, and we want to write a general term for that sequence, and also a recursive formula if we can. Okay, so in problem 12, let's see what we've got here. We've got 1, negative 1/3, 1/9, negative 1/27, and so on. Okay, so the first thing that I would say it's important to recognize about this sequence is that it's what's called an alternating sequence. Okay? It's bouncing back and forth between positive and negative values. And so that's why I was talking a few minutes ago about having that -1 to the n power or to the n plus 1 power. So if I wanted to start to construct this, let's see, a sub n, I'll have -1 to the n plus 1 power. So that'll make this start positive, right? And then the second one will be negative and so on. And then the denominator is just powers of 3 over 3 to the n power. So that's one way you can do this. You can kind of put these together. Oh, let's see here. If I do that, then the first term is going to have a 3 in the denominator. So I need to make that n minus 1. Okay, so that when I put so then a sub 1, so that'll be positive 1, and in the denominator, that'll be 3 to the 0 power, which is also positive 1. Okay, so having done that, there's a simpler way that you can represent this. You can just call this -1/3 to the n minus 1 power. So that way, a sub 1 is just going to be -1/3 to the 0 power. So there's our 1 as the first term. And then a sub 2, -1/3 to the first power, and so on, and then all the other terms will match up. These are both equally correct. There's nothing wrong with either one of them. This one, I think, is just a little bit more straightforward. Okay, now if we wanted to do a recursive definition for this, let's see. So this is a general definition, and the recursive one, let's see here. We would want to say, well, say a1 is equal to 1. Now something like this, where you've got an exponent happening, what that means is that you have a constant multiplier. Okay, so each term is going to be the term before it times some kind of constant multiplier. So a sub n is going to be an minus 1, in this case, times -1/3. Okay, so then you multiply the 1 times -1/3, it'll give you that. Multiply this times the -1/3 to give you positive 1/9, and so on. Let's see here. I think that's all we need to worry about for this one. Okay, let's see. Let's look at problem 14. So problem 14, we've got this sequence 5, 8, 11, 14, 17, and so on. And you can see there's a constant difference. In that previous problem, problem 12, there was a constant multiplier, and that was what's called a geometric sequence. And here there's a constant difference, and this is what's called an arithmetic sequence. Let's see. So if there's a constant difference, this works like a linear function, right? Except that we're only going to be working with the whole numbers, right? So a linear function looks like that. An arithmetic sequence looks like this. It's exactly the same thing, but it's discrete, okay? It just has these discrete points instead of encompassing the whole line. And the constant difference here acts as the slope. It plays the same role that the slope in a linear function does. So, if we want a general term for this, a sub n is going to be 3 times n. And then if we want a1 to be 5, then we have to add the y-intercept, what would be the y-intercept in a linear function on there. In this case, it would be 2. Okay? So we'll say 3n plus 2. So that way, this is 8, so that's 3 times 2, yeah, okay, plus 2. So there's our general term, 3n plus 2. And in the recursive, definition, we say a sub 1 is 5, and then an. Now, in the previous example in number 12, where we had a geometric sequence, we had that constant multiplier, okay, and that was how we created the recursive definition. In the arithmetic sequence, you've got this constant difference, and so all we have to do is just add 3 on to the previous term to get the next term. Okay? All right, let's see here. Problem 16. So problem 16 is kind of interesting. It's very closely related to problem number 4 on the front of the handout. So, problem 16, we start off with 1, 0, negative 1, 0, 1, 0, negative 1, 0, and so on. Okay, so like I said, this is very closely related to that cosine n pi over 2. And you could shift that sequence to match this one. You could call this, let's see here, general definition. You could call this, now if we just did n pi over 2, that would start with a 0, and that's not what's happening here. Okay, so if we wanted to shift it, so let's go back and look at the unit circle here. And remember that the x is the cosine and the y is the sine. Okay, so for this one, we were starting up here with the 0, negative 1, 0, 1, 0, negative 1, 0, 1, and so on. If we wanted to shift this back, we could do kind of the same thing that we did with that negative 1 to the n power, right? So if we wanted to start here, we could just make this n minus 1 times pi. And that way, for the first term, this would be 0. Cosine of 0 would be 1, right? Then for the second term, it would be cosine of 1 pi over 2, and that would give us the 0, and so on. So that works fine. You could also fall back on the sine, right? Because the sine is the y-coordinates, and so that starts at 1, 0, negative 1, 0, and so on. And so we could just call this sine n pi over 2. So these are both correct. They're both equally correct. Now let's see. If we wanted a recursive definition, that, off the top of my head, I am not sure how to come up with a good recursive definition for this. Because it starts out simple enough, right? You're just subtracting 1, right? You're just going, oh, to get to A2 is going to be A1 minus 1. And A3 is going to be A2 minus 1. But then A4 is going to be A3 plus 1. And A5 is going to be A4 plus 1. And then it's going to switch back to being negative again. So maybe there's some way that I could build a recursive definition based on this stuff. But really, in the end, I'm not going to worry about it too much. Okay, so that's it for this introductory assignment on sequences. In the next couple of videos, we will look at finding the limits for these sequences, which goes back to a lot of the ideas that we talked about back in fall term. Okay, so I will get another video ready for you in the next day or so. Thanks.